Okay. PowerPoint's hard. Okay, nice to see you guys. Glad we still have some people coming to lecture, a few. Tell your friends that I'm lonely. It'd be great if they came. This is always the curse of putting lecture videos online, like throughout the semester. This is what happens. In any event, I'm glad you guys can make it. So in terms of course announcements and things, we actually did manage to write a quiz, so it'll be posted hopefully basically at the end of lecture today. As usual, it's very straightforward. Requires you to just logic through the content of the last 2 weeks of lecture this time, since we managed to forget last week. Other than that, you have a homework which is due, I believe, this evening. Yeah. Yeah. I've seen like 1.5 functional homeworks in my office hours so far. So like we're getting there, which is fantastic. So for the remainder of you, I encourage you to swarm Chris's office hours after lecture today, and I will watch with entertainment from my office nearby. Beyond that, and the new homework is out too. So we've posted that. I look forward to seeing the typos that Chris and I have added to this homework. I have. Sorry, Chris doesn't make typos. Beyond that, we do have a midterm coming up on a day that is not today, and we didn't quite sync on that, but we will share you the midterm date soon. It's on the course calendar, so hopefully it's already marked in your schedule as well.
October 26th.
Oh, the 26th. Oh, good. For some reason, I had it in my mind it was next week, but it's not. Fantastic. Good. And again, remember, I think you've already seen on the homework a little bit, like this course is the first time it's being offered. It's not totally calibrated. Some things are likely to be too easy, too hard, but at the end of the day, we're here so you learn and you get stuff out of it, and hopefully we'll all have a fun time together learning numerical methods. Any questions about organizational, logistical stuff? Cool. As always, I encourage you to get an early start on homework 3. At the very least, download starter code, give it a run. I think in this case, the starter code is pretty non-controversial, but yeah, still worth doing. And then the data set is in there too in the zip file? Cool.
So when you decompress the zip file, it might be a little bit big. I think it's like 400 megabytes total. So I guess these days it's not a huge amount, but
yeah.
Just be warned, it's not a tiny file.
Okay, so there's a 400 megabyte file you got to download with a very small PDF inside of it with the problems plus a giant data set.
Yeah.
Big data. It's 400 megabytes. All right, that's like almost a CD-ROM.
I know.
Okay, any questions, comments, concerns? Good pumpkin spice recipes? Halloween costume suggestions? I got invited to a Barbie-themed party on Friday, so I ordered something, and we'll see if it fits. Amazon. Oh, you're right. We have a group outing the same day. It's like kind of sailing adjacent. I could have just a hot pink thing for the whole day. Yeah, and my partner agreed to get a matching one. This is a big week for me. Okay, so in any event, right. So today in lecture, we are going to continue our discussion of the SVD, the singular value decomposition of our matrix. If you recall, we can take any matrix A. This is sort of one of our first decompositions that is matrix agnostic. And we can decompose it as the product of U, sigma, and V transpose, where U and V have orthogonal columns, and sigma contains just a diagonal of positive values. Those values are called the singular values of A. Remember that we did have a few different versions of A, of the SVD, depending on whether we include the 0 singular values or not, right? And so the sort of most generic version has U and V as square matrices, and sigma has a bunch of padding, but we can also kind of remove stuff if we don't care about all the zeros floating around. Okay? Now, basically, whenever you're encountered with a problem in linear algebra, or in life, really, the very first thing that you should do is plug in the SVD and just see what happens, just as a good life philosophy. So, for example, let's say that I want to solve a linear system of equation, or I want to solve something underdetermined, or I want to solve something overdetermined, like a least squares problem. In our previous lecture, we kind of justified that this optimization problem actually kind of encapsulates those 3 cases, right? Because the constraint here ends up fully determining x in the case where A is invertible or overdetermined. And then when x is underdetermined, then the objective function takes over and gives me the smallest norm solution among the multiple ones, right? And essentially, right at the end of our lecture, we showed even this kind of crazy looking optimization problem we can solve with the SVD, and that led us to a particular definition of an object called the pseudo-inverse, which uses this little plus sign instead of -1, which is sort of a generalization of the inverse of a matrix, where we invert kind of in the subspace where we know how to invert, and we just zero out the subspace where we don't. Hopefully we kind of remember that story. But if you think about it, the pseudo-inverse is an extremely generic object. Incidentally, is the pseudo-inverse a particularly stable object to compute? So let's think about it just for a minute, because I think that the pseudo-inverse is something that gets thrown. For some reason, like numerical analysis, people have this like mild blind spot where they're like totally fine talking about pseudo-inverses, but it's actually something that like requires a bit of delicate handling. So in particular, what is sigma plus? Well, remember, for one, it's a diagonal matrix, so everything else is 0. But there's sort of two cases, right? So sigma plus is equal to 1 over sigma I if sigma I is not equal to 0. And what is it equal to otherwise? 0. Okay. So let's say I take a sequence of matrices that approach a singular matrix. Right? So I get a bunch of matrices, they get closer and closer and closer to something that isn't invertible. So in other words, one of the singular value goes to 0. So think about what happens in that subspace. So for a long time, sigma plus puts 1 over sigma I here. Remember, sigma I is going to 0, so what is this value? Big, right? And then suddenly, sigma I hits 0, and then what happens? Well, it becomes 0. So I have a plot that looks something like, you know, this. So so let's say this is sigma I. As sigma I approaches 0, the coefficient in front of it gets really large, and then I have like that. So if I have a matrix and I slightly perturb it a little bit, then probably I'm going to wiggle around the singular value a little bit. Then just a thing to keep in your mind is that the pseudo-inverse can change quite a bit. Yeah? And so this isn't somehow like a magical solution that fixes issues like ill conditioning. It's more likely that this is used to kind of bridge the gap between tall and short matrices, because those singular values are kind of stable, right? Like there's some singular values that are 0 because my matrix happens to be non-invertible, but it's square anyway. And there are others that kind of have to be there because my matrix is like taller than it is wide or something. And so that second category, like this thing can handle relatively well. The first one, like numerically, you have no business computing. So in any event, that aside, the pseudo-inverse is a really nice matrix. Has all kinds of fun properties. If A is invertible, then it's just equal to the inverse of the matrix. That should also give you a hint, like, is this an easy object to compute? Well, no. I mean, we already know that inverting matrices is kind of expensive. But it actually also can handle underdetermined and overdetermined cases, which is kind of nice. Cool. Any questions about our story so far? This is just a quick review from last time. See that basically, in some sense, this is taking like a big chunk of the previous linear algebra lectures, and algorithmically, like if you have the SVD, you can solve linear systems, right? So, yeah. Tall versus wide. Yep. Ah. So overdetermined means that your linear system probably doesn't have a solution, right? Like you have too many rows. So in that case, it gives you the least squares solution.
Okay.
But like least squares and least norm are not the same. Oh no, did I type the wrong thing? Oh no, this is correct. No, I did it right. Sorry. So here's the thing. An underdetermined matrix might still not have a solution. So think about 0 times x equals 1. The 0 is underdetermined, but that system still has a least squares problem hiding in it because I can't satisfy the right-hand side. So what ends up happening in the pseudo-inverse is that's perfectly fine. What it says is in the space where I can solve stuff, I get the least squares solution, and where I can't, I just zero it out. Yeah. Great question. Yeah. This is, for once, I managed to get it right. Yeah. Okay, so this is like yet another example of just the kind of stuff that you can do with SVD. In fact, there's a whole class of things called matrix functions sometimes, which oftentimes we evaluate using SVD or eigenvalue decomposition, and this is a simple example. Oftentimes for matrix functions, you really need your matrix to be symmetric, but that's an advanced topic in numerical math. Okay. So just for fun, I thought I'd give you a few other examples of things we can do with the SVD. And one thing SVD can do is, once I have the SVD, I can do some computations with this matrix quite easily. So for example, so let's say that I factor my matrix using the SVD, because that's what we're doing today. A equals U sigma V transpose. And now I think of U as a bunch of vectors, like U1, U2, and so on, times sigma, times V transpose. So like I can think of this as a bunch of vectors transpose, like V1 transpose, V2 transpose, and so on, like that. So in other words, notice that the V's are still columns of big V, but then I've transposed it. Does that make sense? Well, if I think about it, then I could write down an expression for A in terms of the U's and the V's just by using matrix vector product. So in particular, remember how like products work? They go like that. So in particular, you know, thankfully, remember that sigma here is diagonal. So really, it's just kind of like weighting the rows here. So at the end of the day, I get a really interesting form, which looks like this. It looks like the sum equals 1 to L. Here, I'm going to use L as a placeholder for number of singular values. That way I can deal with the non-square case. Of sigma I, and then what I'm going to end up with is Ui Vj transpose. So this is a sum. Oh wait, that was not quite right. Ui Vi transpose. Right? Do you guys see that? Like, notice that I get like a U V transpose, and like this is a product all the way down. So this is just another way to write out this product here. So here, L is equal to the min of n and n. This is just a lazy placeholder. In fact, I can even take L to be less than that if I have 0 singular values. And then this is just a reshuffling of this matrix product. It's a different way to write it. Okay, so why does that matter? Well, remember like when we were doing eigenvalue decomposition was another good example. I have like ax lambda equals lambda x. I take a vector and I write it in terms of all the eigenvalues. And then if I multiply it by the matrix, the eigenvalue kind of tells you, in some sense, there's like an importance sampling, importance weighting happened there, right? If I have really tiny eigenvalue, then when I multiply by the matrix, in effect, I'm just like zeroing out that component of my vector, right? So something, in particular, Ui and Vi, these are unit vectors, right? So the only scaling that's happening is with the sigma. Remember, we've chosen sigma 1 is greater than or equal to sigma 2, greater than or equal to dot, 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 greater than or equal to sigma L. Yeah? So first, if I wanted to compute A times X, what could I do? Well, if I have AX, then in this particular form, it's equal to the sum I equals 1 to L of sigma I Ui Vi transpose X. Obviously, all I did was put an X on both sides. Okay. Let's say that I parenthesize it this way. So how much time algorithmically does it take to compute Vi times X? This is a dot product, right? At the end, hopefully you guys are recognizing this pattern right now. How long does it take to compute a dot product if I have n entries? N, right? I just loop over the elements. This is not a trick question. Okay, so then this becomes a scalar. How long does it take for me to take U and scale it by, I guess, sigma times this thing? Also n, right? I just loop over the elements. So computing one term in this sum takes order n time. Okay. So let's say I want to do matrix vector product really fast, and I'm okay with it being approximate. What could I do? Well, conveniently, this sum actually is kind of ordered. Right? Do you see that? Like, the first singular value is really big, the second singular value is a little less big, and so on. So like, what's going to be the weight outside of like the 100th term in this sum? Well, likely it's going to be pretty small, right? So in particular, a very common strategy for accelerating matrix vector product, if you happen to have the SVD, is to do the following, and we're going to kind of refine this idea in a minute, is maybe to sum up to some other k, which is less than L, of the same thing. Oops, there's a UI missing. UI, that one's a U. Oh no. Okay. And so the basic idea here is I just remove terms from the sum, but like since those sigmas are probably close to 0 anyway, I haven't really changed the value a whole lot. We're going to formalize this in a minute. Does that strategy make sense? And notice I just made my algorithm faster. I basically just sliced out, order n calculations each time I removed one of these terms. But here's kind of a cool thing. What do we remember about our eigenvalue algorithms? Other than QR iteration, for the most part, our algorithms for computing eigenvalues gave me one at a time. In fact, they gave me the biggest eigenvalue. Yeah? So do I really have to compute the full SVD of a matrix in order to make this trick? Like, let's say that I know a priori I'm only going to want to have like 10 terms in this sum. Then notice it's enough for me to compute just the top 10 eigenvectors of A transpose A and like just discard them after the fact, and I already get a reasonable estimation of matrix vector product. Isn't that sneaky? Now, probably for matrix vector product, this isn't terribly useful because like, what is my algorithm for computing matrix eigenvalues? Well, it involves computing a lot of AXs. So like this as an efficiency technique is kind of dumb, right? Because in order to get the SVD, I kind of have to do the thing that I said I didn't want to do. Yeah. But there's a case where that might not be the case, which is the following. Say I want to do A inverse X, and moreover, I want to do this for a lot of X's. So I'd like to kind of pre-compute A inverse. But of course, pre-computing A inverse, we know is problematic for like 100 different reasons. Like it's a little unstable, it's probably a dense matrix, even if A is sparse. Like actually, by the way, the matrix you invert in your homework due today is a great example. If you try to compute the inverse, your laptop will probably crash. So you have to use linear solve instead of invert and then multiply. Okay, but notice, what is A inverse of X? So we have this convenient pseudo-inverse formula, which says that basically inverting a matrix amounts to replacing the sigmas with 1 over sigmas, right? To the minus 1, ui vi transpose X, like that. Now here's a really cool idea. What can I do? Well, remember, we have algorithms like inverse iteration for eigenvalues that can give me like the small singular values. And of course, now by computing 1 over the sigmas, I've reversed their order, right? The biggest terms are now at the end of my list, right? But I could use inverse iteration to compute the top few dominant terms in this sum, and then just slice out the remainder. And now I have a very fast approximation of A inverse that I can apply relatively quickly. Does that make sense? This is a very common technique. And in fact, by the way, it gets kind of echoed in a lot of different spaces. Like for instance, physicists often talk about like solving the differential equations you see in physics just like in the kind of low frequency domain. And in physics, oftentimes there's an identification between frequency and eigenvalue, and they're essentially doing very similar kind of truncation, just in a different language. In case you want some fancy language to describe what we just did here, this matrix UV transpose is like kind of a new one that we haven't seen a whole lot in our lectures yet. Notice we've seen like U transpose V quite a bit, right? That's a dot product, but that's not this object, right? This is flipped the other way. So this is an n by n matrix, right? But it's rank 1. So this thing has a name. It's called the outer product of U and V. Sometimes it's denoted with this little circly X thing. I believe there's even like special little piece of code out there in like PyTorch or whatever your favorite numerical library is for computing outer products. I saw it in my office hours. And so essentially what we've done is you can say, if you want to be fancy about these summations, you can say, well, what is the SVD doing? It is decomposing a matrix into the sum of a bunch of outer products. You see that? This is kind of nice. It's basically the sum of a bunch of rank 1 matrices. And that's really what's hiding behind the SVD. This is just an alternative way to describe this. And then again, we can compute matrix vector products in all kinds of different ways, truncate small things, and do our sum quickly. And that includes for solving linear systems. Yeah. So that was our trick. And in fact, we don't even have to compute the big or small sigma I at all by using some of the algorithms we talked about for eigenvalues that only give you like 1 at a time, right? So like I can compute the top 10 singular values of a matrix much more easily than the full set. It's not like I have to do all of SVD and then throw away 2/3 of it and just do this sum. That makes sense? Any questions? Yeah. Oh, you're absolutely right. I'm sorry. I swapped U and V. There you go. Yeah, you're right. Yeah, so again, if we have U sigma V transpose, then A inverse is V sigma inverse U transpose. So the roles of U and V swapped. I'm sorry. I should hopefully, oh gosh, is that in the slides? Did I? Oh no, I got it right in the slides. I just said it wrong. Sorry about that. Yeah. Oh, and then instead I wrote 2 V's, which is the worst possible thing. That one's a U. Okay. Good catch. Thank you. Any other questions or stupid mistakes the instructor made? It's reasonable. I make a lot. Okay, so this is an approximation, and we have an intuition that it's like a good one because like somehow slicing out small sigmas feels like I'm like slicing out the kind of boring part of my matrix. One question you might ask is, can I formalize that idea? Like, can I actually prove something? And the answer is, of course, yes, because I wouldn't be asking it if the answer were no. And in fact, this is a very famous theorem. It's one of the earlier ones in the sort of codification of linear algebra. This is called the Eckert-Young theorem. It says the following. Actually, this morning I got nervous and I rephrased it a tiny bit in the textbook. I'll upload a revision. But essentially what it says is, let's say I want a rank K approximation of a matrix A. So in other words, I'd like it to be the sum of at most K outer products with weights in front of them. Then among all of the possible rank K approximations, this particular one that we've written here is the best approximation, and actually both L2 and Frobenius norms. Kind of surprising. Well, it's actually not surprising at all. No, I'm sorry, I take that back. This is sort of like what else would it be, is the kind of theorem I would classify this as. But it's good to know, right, that like this isn't just a heuristic. This is actually sort of as good as you can do. Does that make sense? Do we want to prove this? Yeah, let's prove this. This is an easy proof. Anybody have any ideas how we should prove it? The math student is gone. He would engage. Okay. He warned me he was leaving for a few weeks, and wanted to make sure I was okay with that. Okay. So in particular, here's our usual setup. So right, what we're going to do is sort of just take the rank K approximation that we've already been playing with, and then we're going to compare it to just a generic rank K thing and show that one of them, you know, the norm of this difference is big. Okay? So in particular, let's say that we take A as usual as U sigma V transpose, like that. And once again, we're going to sort our singular values from big to small. And sigma, I guess, L. Okay. So we're going to define AK to be this rank K approximation. So I equals 1 to K of sigma I UI VI transpose. So notice that AL is equal to A. Cool? All right. So the first thing we're going to do is just write down a nice expression for the error when I approximate with AK. And then I'm going to write down a generic expression for error when I approximate with something else, and then compare the two. That's our strategy. We on board? This is like, you know, another kind of toucan Sam like proof here. Like we just follow our nose, write down what we know, and eventually something comes out. Okay, so, and by the way, we're going to prove it for the spectral norm. The Frobenius norm proof is basically the same, but requires a triangle inequality because Frobenius norms are like not very nice. Or rather, they're very nice to compute. They're not very nice to prove things about. Okay, so we know that A is equal to the sum I equals 1 to L of sigma I UI VI transpose. And now we're subtracting off K, which is the sum I equals 1 to K sigma I UI VI transpose. Like that. 2. Right, so all I've done so far is plug in our expressions, right? This is A, K, and this is A. And of course, these two sums overlap, right? So remember the L here. So K, we're going to say is strictly less than L, because that's the interesting case. Okay? So in particular, this is nothing more than just the sum of basically the remaining terms. So it's equal to the sum from I equals K plus 1 to L sigma I ui vi transpose. Cool? All right. So this object is a matrix. I'm trying to take its spectral norm. And I claim that we can just eyeball it. Now, why is that? So remember, like, what is the spectral norm? I take the matrix and I multiply it by a vector of length 1, right? And then I compute the norm of that vector, and I want to take the soup over all vectors. Okay? So take a look. So the sigma i's are sorted from sigma k plus 1 to n, right? And I can get something that looks, I claim that basically this norm is going to equal sigma k plus 1. Why is that? Any ideas? So first of all, notice that I can get it if I take or rather, if I take, so let's call this matrix M. If I say x is equal to, I guess, v k plus 1, like that, then notice that I'll actually get this expression. Or rather, I'll get sigma k plus 1 that comes out of the norm. Do you see that? I can write it out. You look puzzled. I'll write it out. So then mx is equal to the sum I equals k plus 1 to L of sigma I ui vi transpose times v k plus 1, like that, right? But notice, remember the v's are orthonormal set, right? So this value is binary. It's 0 when I is not equal to k plus 1, and it's 1 otherwise. Yeah? So this thing is really equal to sigma k plus 1 times u k plus 1. And this thing, the norm of this thing is just sigma k plus 1. Right? So clearly I can, this value is at least this big. I claim it can't really be bigger. And I think that's actually quite intuitive, right? Because these are sort of scales in front of unit things. I'll let you check that one at home. Cool? So what did we just show? We showed kind of a nice fact, by the way, that the approximation error of approximating a matrix with k terms in the sum is just equal to the very next singular value. This is the part that the Frobenius norm proof is not quite so nice. But you can get there too. Okay. Any questions so far? So now what we want to show is if I approximate with some other b, and b is rank k, that the error that I get, the difference here, is larger, right? So in particular, so let's say b is equal to x, y transpose, right? Because it's rank k, we know that we could write it this way, where x is in R m by k, and y is in R n by k. Right, so essentially this is just saying, this is a fancy way of saying b is rank k. Okay, I'm going to erase this little note here. Okay, now there's like kind of a sneaky thing we're going to do, which is the following. So define a new matrix vk plus 1, which is going to be v1 to vk plus 1. So we're just going to take the first k plus 1 columns of v, which is just the definition. Okay? So now, here's going to be our trick. I claim we know that the following thing has a null space. Y transpose vk plus 1. Why is that? So vk plus 1, how big is this thing? Well, it's n by k plus 1, right? Right, because there's k plus 1 columns, each is in Rn, just by construction. Yeah? How big is y transpose? And we know what y is n by k. So y transpose, this is k by n. So first of all, notice that this matrix product makes sense. That's a good thing. But also notice that, so the product together is going to be k by k plus 1. So it's a matrix that sort of takes a higher dimensional space and goes to a slightly lower one. And we know for matrices like that, in other words, it's a wide matrix. Remember, we showed that those matrices always have null spaces. So we know this thing has a null space. So in particular, there exists a vector z such that y transpose vk plus 1z is equal to 0, and z is non-zero. Right? That's the definition of null space. Everybody with me so far? This is a really sneaky little trick. I guess Eckert and Young were sneaky dudes. Okay, so in particular, we're going to scale so that the norm of z is equal to 1. We can do that because we know z is non-zero. Okay? All right. Why is this going to be useful? Essentially, what we're going to do is we're going to try to bound the difference between a and b and show that it is upper or lower bounded by the difference between a and ak. Right? That's our overall strategy here. And probably you can kind of see where we're going with this. We're going to use z as the vector that we'll use to bound the spectral norm. Okay, so let's do this in more detail. Sorry, I just gave a spoiler alert. I'm sorry. Oh no. Or no, I did the opposite of that. I gave a spoiler without the alert. You were unalerted. Caught by surprise. Okay. So for our last trick, we will prove the Eckert-Young equation, which is basically a ginormous chain of inequalities. Put on your seatbelts, everybody. So we have a minus bk. And again, eventually, 2 norm. And eventually, right, what we want to show is that this is bigger than or equal to a minus ak. Right? I'm sorry, there doesn't need to be a k here. Right? That's our goal. If we do that, we've proven the theorem. Right? Because this is saying that b is a worse approximation than our formula. Okay. So it's important not to think here. So let's just plug in our forms for a and b. Oh, and even before that, so let's maybe square the norm for convenience. And let's plug in the definition of the spectral norm. So what is that? Well, it's the max over all q, whose 2 norm is equal to 1, of the norm a minus b, or a minus b times q squared. Right? So far all I've done is plugged in the definition. Is there a Roomba outside of this room that's lost? I think that's what that noise means. Like, it sounds like when my Roomba gets upset in the middle of the night. Okay. So this formula is a max. So if I plug in any q, we know that this thing is, like, if I take this expression inside of the max and I plug in any q, that is a lower bound for the max. Right? So in particular, if I plug in, I'm going to put q is equal to vk plus 1 times z, like that. I'm going to make a very clever substitution. Right? So then since we took the max over all q, in particular, if I plug in this q, I get a smaller value, because the max by definition is the biggest possible one. Right? So what do I get? I get a minus b, like that, vk plus 1 z. Okay. Everybody with me so far? Like, at least you believe that one could make this chain of inequalities. You might not see where we're going with it yet, but like, that's okay. Okay. So from here, we're just going to start plugging in everything we know and simplifying. So in particular, what is this? So A is U sigma V transpose by definition, right? And then what is B? Well, it's equal to X, Y transpose, right? That is like our sort of counterfactual here. And then we have a V, K plus 1 times Z. Whew. Okay. What should I do next? Why did we choose Z? Well, basically, we only know one thing about Z, right? So we multiply it with a particular matrix, we get 0. What is that matrix? It's like literally on the board. It's, you're looking right at it. It's right here. V. You guys are so quiet. It kills me. So this is Y transpose times VK plus 1 times Z is equal to 0. So this expression I'm pointing at, right? Notice, y transpose vk plus 1 z. So what is the second term if I expand this product? 0. Yeah, hooray. So let's carriage return, CRLF. So what is that expression equal to? It's just equal to the first thing. U sigma v transpose times vk plus 1 times z. Cool? Now we're cooking with gas. Like, this kind of feels like what we wanted, right? Because notice this is like some combination of the v's. And then we've got the weight sigma, and somehow this combination knows something about sigma k plus 1. Yeah? So we're like, we're doing pretty good. Okay. In particular, I claim that this thing is nothing more than the sum I equals 1 to k plus 1 of zi squared sigma I squared. Let's see if we can logic our way through that. Okay, so first of all, pre-multiplying a vector by an orthogonal matrix doesn't change its norm, right? So we can basically ignore the u there, right? And what is this thing? Well, this is the inner product between all of the v's and then the first k columns of v, right? Or first k plus 1. So this kind of looks like the following. It looks like 1, 1, 1, 1, and then a bunch of zeros. Yeah? That makes sense? So at the end of the day, and then I've got z1, z2, whatever. So if you think about it, this product is just identifying the first couple terms in this sum, and then it gets scaled by the sigmas here, right? So that's what justifies this formula here. Cool? Okay. So what do we know? We know that it's some weighted average of the zi's, or not weighted average, but a weighted sum of or I guess the sigma i's with weights that are the zi's. Okay. And we know one additional thing about this stuff, which is that we know that z, we chose this norm to be 1. Okay? So in other words, like, these z squareds, they're all a bunch of positive numbers and they sum up to 1. Right? So it's some weighted average of the first sigma i's, right? What is the way that I can make this thing like the biggest or the smallest? Well, like clearly, remember the sigma i's are ordered, right? So sigma 1 is bigger than sigma 2 is bigger than sigma 3. So the most weight that I can put on the tail end of the sum, the better. That make sense? So in particular, I claim this is greater than or equal to sigma k plus 1 squared. You see that? Because that's the very last term in the sum if I had a z weight in front of it, and all the z's have absolute value less than 1. Cool? Well, isn't this convenient? If we look at the previous board all the way up there, well, we have an expression for sigma k plus 1. It's just equal to a minus ak squared. Cool? So what do we show? We show that for a generic b of rank k, the difference between a and b is upper bounded by the difference between a and ak squared. But of course, we can take the square root on both sides because they're positive. And that actually is exactly the Eckert-Young theorem. Cool? Isn't that neat? So like in other words, like for instance, one of the applications that we think about for SVD quite a bit, in fact, I think what most computer science students think of is principal component analysis, right? And remember, what is PCA? It's like saying I pick out the rank K subspace that best explains my data. Now you can kind of see why the SVD is relevant to PCA, right? Because it's saying find me the rank K thing that best approximates my data, like in the columns of a matrix. Yeah? So this is directly relevant to that. Any questions? Cool. In fact, I mean, this is just the beginning. I mean, there's so many things you can do with SVD. So here's some more. Here's some expressions for different things I might do to the matrix. For example, the Frobenius norm is just the sum of singular values squared. The 2 norm is the biggest singular value. In fact, this proof kind of sort of used that fact. The condition number is the ratio, the biggest to smallest singular value. So all of these things, I think, are just identities that, like, maybe we'll skip proving here, would be fantastic ones to prove on your exam, for example. Okay. Any questions so far? Incidentally, the course notes don't contain this proof. I got nervous that I didn't have enough lecture content today, so this morning I read it. But for once, I think it's actually correct. Neat. Okay, so for our final trick here, we're going to solve one more kind of computer science looking problem today. And that is the following. And again, it's going to be solved with the SVD. Ta-da! And that's rigid alignment. And sometimes it's called Procrustes problem. So here's the basic idea. This actually is from my universe because I work a lot on 3D problems. So here I've got this 3D hand point cloud thing. I have two collections of points. And maybe for now, somebody has kindly marked a few pairs of points, like the tip of the thumb on the one point cloud and the tip of the thumb on the other point cloud, and a few others. And so my task is going to be to find the rigid motion that takes these two point clouds and then aligns them to one another. Right, so a very typical application here would be I have a 3D scanner, and I walk around a shape, and I scan it like a few different times. Right? And so as I do that, I get sort of different parts of the shape, like what's visible from the camera, but they're all kind of rotated from each other because they're in the frame of the camera, and I don't know how the camera's moving. And so after the fact, I might want to make a whole 3D object, then I mark a few landmark kind of correspondences and align these things together. Does that make sense? This is also one of two steps in a famous algorithm called iterative closest point, which says maybe I didn't mark the pairs of points that were in correspondence to one another, so I'm going to update those as well, but maybe we'll defer on that discussion for now. So for now, we're just assuming somebody has clicked pairs that we know match together. Actually a reasonable assumption. Any questions about the sort of input and output? So basically two collections of points that are in correspondence to each other. And our output is a rotation and a translation and one onto the other. So let's do a little modeling. So in particular, let's say that I have a bunch of points, x1 and x2, that are paired together. So think about like the tip of the thumb on the first hand and the tip of the thumb on the second hand, and like the middle of the palm on the first hand and the middle of the palm on the second hand. A whole list. So I indexes which one of them, and then the 1 and the 2 are for the first hand and the second hand. Cool? Then my task here is to find a rotation and a translation, so R and T, so that when I take my points in x1, I rotate them by R, and I translate them by T, I get the points in x2. Does that make sense? So let's make sure that we understand this objective function, because I use some cute notation here. Is it okay if I erase the board? Cool. I love that the people who always respond to that are the ones that are just looking at their laptop anyway. Okay, so let's say that I have the xi, right? So then if I rotate x, what's the notation I have? 1i, and I translate by t, like that. Right, then the obvious objective function here is the sum I equals 1 to, I don't know, n of the norm between that and x2i squared. Okay, there's our least squares problem. It's not quite least squares because, of course, we're constraining R to be orthogonal, right? And actually, from your homework, conveniently, we know that that means secretly that R is a rigid motion. Okay. So this object, the way that I've written this expression here is a vector, right? It's a difference of two vectors. And what's on the screen is a difference of two matrices. So essentially, all I've done here is notice that, let's say that I make one big matrix X, which is X1, which is like X1, 1, X1, 2, and so on. And similarly for X2. So like I'm just going to take all of my points and stack them together. Then if I pre-multiply this thing by R, then I've just rotated each of the x's. But now I also have to add t. But t is a vector. So this is just a cute mathematical trick. So this bold 1 here is the vector of all 1s. So what is t times the vector of all 1s transposed like that? Well, one thing you can convince yourself is this is just t copied n times. Okay? So this entire expression here is equal to R x1 plus t1, which is just saying add the same translation to each of our points, minus x2. Okay. And I've sneakily moved back to the Frobenius norm here because that's going to make my math a little easier. Everybody with me so far? Cool. I claim this problem can be solved with the SVD. Not totally obvious the way I've written it here. In particular, part of my variables, like the R part, this part looks like a orthogonal matrix. So this like feels like maybe something that would come out of SVD, but the T is totally unconstrained. It's just a translation. It could be anything. And so we've got to do a lot of massaging on this problem before we're going to get it into the form that we like. Does that make sense? You might notice some commonalities between this and some problems on your homework. Okay, so, right. So let's optimize. So at the end of the day, we've got to be optimal with respect to R and T independently. And so our strategy is going to be first to optimize with respect to T, because that one's unconstrained. We'll just take the derivative with respect to T and take that equal to 0. We're going to get a nice expression for T, plug it back in to eliminate it, and then optimize for R. That's going to be our strategy. And along the way, we're going to make friends along the way. And we're also going to learn something that I forgot. The orthogonal Procrustes problem. Okay, so in any event, we're going to make use of some of the fun matrix expressions that some people in my office hours have struggled with, so this is good timing. In particular, there's a fun expression for the norm, the Frobenius norm of a matrix. So if I have A Frobenius norm squared, this is equal to the trace of, how did I write it? A transpose. Like that. This was actually in lecture 1 of this course. I'll let you go back and double check this formula later. Okay, but you can get it just by like writing out the elements of this thing and then writing out the formula for the trace, and you'll see that these are the same. And we like that because traces are like really malleable mathematically. We can do a lot of stuff with them. So it's often useful to convert expressions like this into this form. Sound good? Okay, so now we have to do something excruciatingly painful. I'm really sorry. Which is we have to take this Frobenius norm here, and we're going to write it in this trace, and we're going to expand out a ginormous product. Okay? So, in particular, this is equal to the trace of this thing times its transpose. So we've got a Rx1 plus T1 transpose minus x2 times this thing transpose. Rx1 plus T1 transpose minus x2, all of that transposed like that. Okay. Unfortunately, we now have to, actually I'm wondering if I can be sneaky about this. Do I want to be sneaky about this? No, we'll just expand the product. I think you could probably differentiate this thing with respect to T in kind of a sneaky way and avoid some calculations we're about to do, but I'm nervous to do that because it's not in my notes. Okay, so in particular, we're gonna do the transposes and the products all at the same time. So this is gonna be equal to the trace of, we have an x1 transpose plus an x2 transpose. So for example, notice that there's r's here, but the r's are gonna end up canceling. We've got a plus 2 rx1 minus x2 times the vector of all ones times T transpose. We got a minus 2r x1 x2, and then plus an n T transpose. Where does the n come from, by the way? Well, like, if you think about it, the dot product of the vector of all ones in itself is going to be n, right? Because it's like 1 plus 1 plus 1 plus 1 plus 1. Okay. So this is essentially the expression you get by taking that thing and just multiplying it out. Whew. But here's the good news. let's say we're optimizing for t. So where are all the t's? We got one there, we got one there. This is like actually not so bad. Okay, so in particular, 0 is going to be equal to the gradient with respect to t of our energy function. Maybe we call it E. Okay, and what is that thing? Well, conveniently, we basically got a linear term here and a quadratic term there. So this is not actually so hard, right? So we have that this is 2rx1 minus x2 times the vector of all ones. So basically just the coefficient in front of the linear term. Plus 2n t, right? Because this is like t squared. Yes, Axel. Ah, yeah. So what happened to the trace? So let's see. This is a function that inputs, like for now, a vector t and outputs a scalar, right? So if you think about it, the derivative of that should end up being a vector, right? So this makes good sense. By the way, if you want to see this very clearly, notice that, like, let's do this term really quickly. So this is the trace of n t t transpose. But remember that trace has this property that I can kind of cyclically permute. And n, by the way, is just a scalar. I can move it out there. So this is really equal to n times the trace of t transpose t, like that. But this is a fancy way of saying n times the norm of t squared, right? Because this is a 1-by-1 matrix. The trace is equal to itself. So really, now you can see why you get 2nt. You can do a similar thing for the first term. Fantastic question. Any others? Well, this is great. So once I know r, I know t, right? That's what this expression tells me. In particular, let's just do it. If I isolate t, I'm going to get t equals 1 over n times x2 minus r x1 times the vector of all ones. Right? So all I did was just rearrange this expression. So who wants to give me a sort of spiritual interpretation of this expression here? Like, what is it telling me about t? Anybody see this? Yeah. Mm-hmm. You rotate first, translate second, but in particular, the translation is quite meaningful. So in general, when I multiply something by the vector of all ones, I'm just like adding up the columns, right? So think about, like, I have a set of stuff, I add them up and I divide by n. It's an average. Yeah. So essentially what it's saying is that the optimal t is the one that lines up the center of mass of x2 and r times x1. Right? Cool. Which is intuitive. Like, somehow the nice thing is this is very geometric at the end of the day. Yeah? So we proved a totally obvious fact. It just, we wrote down so many symbols it became non-obvious. Yeah? That sort of makes sense. Notice, like, if it were something else, that would be, like, kind of strange. Okay. So, good. So now we have t. But sadly for us, our job here is not done. We have to find a rotation. Or flip, by the way. The way that I've written this problem, we're going to allow our point cloud to invert. Notice that the only time that would happen is if somebody, like, made really, really bad marked pairs of points. Fixing that, by the way, is, like, kind of a headache. It turns out, like, it feels like an easy fix to this proof, and it's not. Even though it's an easy fix to the final formula, it turns out. It's kind of surprising. Right, so. Although I was really entertained, one of our students, so there's a problem very similar to this on your homework, right? It's like ask you to find an R that's orthogonal and satisfy stuff. One of our students did the wild and crazy nasty proof by accident for this thing. And then the extra credit problem, which said now add the constraint that the determinant of R is equal to 1, was like a one-liner for him. I've never seen that before. I was impressed. But maybe all of you guys did too. I don't know. Okay. Right, so in any event, now we have to do something kind of nasty. So, like, what do we know so far? We know that if we know R, then we know T, right? So one thing that we can do is take our objective function and think of it just as a function of R, right? We're going to just substitute in this formula for T, okay? Because I know that this is the optimal T. So let's do that. So in particular, we're going to kind of think of our energy function as a function not of RT anymore, but of R, comma, this thing, 1 over n, x2 minus r x1 times the vector of all ones. This is like kind of saying that I only really care about the rotation that is optimal for the thing that also is optimal for translation. Okay. So this is an annoying expression. I'm going to propose. It's okay if you don't want me to do this. I have it in my notes. Do you trust that I copy my notes from the book correctly, or would you like to actually do this product? I do this very rarely. I hate it when professors say, just trust me. But I do think this is a case where this is just, notice that this expression is nasty, but it's just linear in R. So like essentially every time I see a t up here, I'm going to substitute this thing and then expand a giant product. So I'm going to go ahead and write it down. I hope that's okay. It's in the book, I promise. Incidentally, this proof in the first edition of the book is completely false. My bad. I noticed that a couple weeks ago when I was preparing this lecture. So I do encourage you to read the book stuff carefully because I rewrote it and it could easily be, it contains a new set of typos. But I think this one's right. Okay, so in particular, this is going to be a constant, right? Because any term that does not involve r just kind of doesn't matter now. Minus 2 times the trace of r times a bunch of stuff. x1, x2 transpose, then we got a minus 1 over n, x1, 1 transpose, x2 transpose. Like that. Okay? Here's the good news. Even if you don't trust me, you can probably convince yourself that it's 2 times the trace of r times something just by kind of eyeballing this expression up here. Okay? And in particular, I'm going to give this something a name. Let's call it C. Okay? And the good news is that it's computable. Notice that like there's nothing here. Like this is all just simple linear algebra in terms of x1, x2. Right? So let's say this in particular is equal to the constant minus 2 trace r. Now it doesn't look so bad because I just factored away all the nasty stuff. Cool? All right. So what do we want to do? Essentially, we want to maximize the trace of RC. Do you see that? Because there's a minus sign in front of it, and our objective was to minimize before. Cool? So we want to find the R subject to R transpose R is equal to identity. This is actually a very abstract problem. This is called the Procrustes problem, just generically. So given a C, finding the R that maximizes this product, subject to R being orthogonal, is called Procrustes. Anybody know what Procrustes is from, like what the name is? Yeah. There's a Greek myth. Do you care to explain the Greek myth? Because I never get it right.
Yeah, I'm not going to get it right. There's some sort of guy who like likes to do mouse and then has one side bent and cuts off sort of their hand and legs or stretches them to like it's bent.
Yeah, there's like a person that has a bed and the bed is a particular size. You can't possibly go to Bed Bath & Beyond. So I guess, which didn't exist back in the day. It was dark time in Greece and, or Rome. What was that? Bed Bath & Beyond for clothes, but now it's open again. I'll have you know, it got purchased by Overstock.com and it now has a new second life, but they don't take the coupons, which is disappointing. I'm distracted. So Overleaf, Procrustes, Overstock, Overleaf. Procrustes was like a king of some sort. He had a bed. Apparently, he really liked people to sleep in this bed, but if they were short, he stretched them out, and if they were tall, he smushed them in. Why, you might ask? I don't know. It seems like a terrible story, like not even an interesting story, just bad. But, you know, it was, they didn't have video games. So in any event, that's, we call this the Procrustes problem because somebody in their very abstract mind feels like finding the best approximation of a matrix with an orthogonal one is somehow similar to chopping off your feet to fit in a king's bed. If that makes sense to you, that's fantastic. If it doesn't, then join the club. Okay, so what are we to do? Well, this is a lecture on SVD, and it hasn't happened yet. And in general, by the way, this is representative of a very common proof strategy in linear algebra, which is when I don't know what to do, I take the one matrix sitting in front of me and I substitute the SVD and just see what happens. There's a trace, but there is a matrix here. Its name is C, right? So let's compute the SVD. So let's factor, and notice that we can do that because C is written completely in terms of things that we know. Right? So we're going to write C is equal to U sigma B transpose, like that. Okay? This is just a good proof strategy. Anytime you're sitting on your midterm, for example, and you say, gosh, here's a linear algebra problem I don't know how to solve, the very first thing you should do is plug in the SVD and just see if that helps. It'll never make it worse. Guaranteed. Okay, so Right, so what do we have? We have trace of RC is equal to the trace of R U sigma V transpose, like that. Cool? Okay. So here's a kind of nice trick. Remember that the trace of AB is equal to the trace of BA when the dimensions work out. So let's call this thing A and this thing B. And then this is equal to the trace of V transpose R U sigma. Cool? So all I did was swap. So notice this is kind of nice. Because R is an orthogonal matrix, right? That's unknown, but it's orthogonal. U is an orthogonal matrix, and V is an orthogonal matrix, right? So to go to Paul's question, like the trace is doing us a big favor here because it'll let us group together stuff that normally is separated, you know? So let's give this thing a name, shall we? Let's call it R. Did I put a squiggle or a bar in the book? A squiggle, like that. Notice that if I know R squiggle, I know R. If I know R, I know R squiggle. Yeah? So now, like essentially what I'm doing is I'm taking my optimization problem, and notice that I'm just writing successively easier versions of the same thing. So now I can solve the following problem, which is max over R squiggle, which is also orthogonal, of the trace of R squiggle times sigma. Okay. And again, if I can solve this, then I can use this substitution to solve the previous problem. Okay. So it's important not to think here. In particular, notice that the sigma is diagonal. Remember that when I multiply on the right by a diagonal matrix, I'm just scaling the columns. So I can just write the formula for the trace. This is equal to the sum sigma I R I squiggle, like that. Now this proof is, by the way, starting to look an awful lot like our proof of the Eckert-Young formula, by the way. We have a bunch of positive values that are weighted by these R's. Moreover, the R's kind of, they don't add up to 1 anymore, but they have some orthogonality relationship. Whew. Almost there, I promise. So let's say I have a matrix, just generically speaking. I have R tilde, and the only thing I know about R tilde transpose R is that it is equal to the identity. And I look at the diagonal elements of R, right? Because that's really what we care about. So first of all, what are the columns of R? It's tilde. If you think about it, they're unit vectors. Do you see that? Like that's actually what the diagonal elements of this relationship are telling me. It says every single column of R tilde is a unit vector. Everybody with me so far? Can a unit vector have an element in it that's equal to 2? No, right? Every single element in a unit vector has to have absolute value less than or equal to 1. Does that make sense? Everybody agree? I can write that down, but I think the words, relative to the other annoying stuff we've done, that's a relatively easy one. Okay, so in particular, RII is less than or equal to 1, right? So we can say the following, that this thing is less than or equal to the sum of the sigma i's. Or greater than or equal to, sorry. I said the right thing, or said the wrong thing, but I wrote the right thing. That make sense? So we have a minimization, or wait, is it, sorry, no, I said the right thing and I wrote the wrong thing. The sigmas, the r's are less than or equal to 1. So if the sum here is, yeah, sorry. Okay, so here's the thing. So I have a maximization problem and I've upper bounded the objective value. If I can find an R that realizes that objective function, or that objective value rather, then I'm done, right? Because I've shown that it gets the biggest possible thing. Notice, by the way, no Lagrange multipliers or calculus are needed here. This is where, like on your homework, there were sort of 2 paths you could take. One is the really nasty Lagrange multiplier, and then the other is this kind of simple argument. Okay, so this is upper bounded by this value. Can I actually achieve it? So what would that require? That would require RII equal to 1. So I need an orthogonal matrix with 1s down the diagonal. Can anybody give me one? Paul can. He says yes, but he won't tell me what it is. Somebody else? I heard it in here. The identity matrix. Right. So in particular, if we take R tilde equal to I, then there's an equality here. And that's the biggest possible value. Cool? Okay. So R tilde is equal to I, but remember that that's V transpose R U. So in other words, we have that R is equal to V U transpose. Cool? All right. So what do we show? We actually showed a very generic fact about life. We showed if we want to find the biggest possible value of this over all matrices with orthogonal columns R, then what do? Well, I take C, I compute its SVD, and I basically throw away the sigma part and just compute this expression here. Cool? So when we fit all these pieces together, we've essentially just solved our point cloud alignment problem, right? So now this thing gives us an expression for R. Then we have an expression for T in terms of R, right? That's what we did first. So now we have a way to compute all this stuff in closed form. Any questions? I think this is a fantastic example of like, in the absence of knowing what to do, you should compute the SVD, right? And especially when you start seeing orthogonal matrices, you can be pretty sure the SVD is going to show up somewhere. Cool. All right. So the slides basically have the same calculation here. This, by the way, is called the orthogonal Procrustes theorem. Notice that this particular formula allows R to be, for example, -1 times the identity, or even like, like it could invert stuff. So there's a different version of this thing where you say, I want R to be in SON, meaning that like R transpose R is equal to the identity, and the determinant of R is equal to 1. So you can't have a -1. Then you get almost the same thing, but you have to start flipping the signs of the columns of U and V, it turns out. Justifying that formula is a little yucky. This is, I think, sometimes called the WAHBA problem, W-A-H-B-A, if you want to Google it later. But I digress. People in aerospace engineering, for some reason, always call these kinds of things WAHBA problems. It took me a long time to figure out the difference. OK. Right, so at the end of the day, if I want to align 2 point clouds, it's quite simple. We can do it in 3 steps, right? We have basically a data set, x1 and x2. These are, remember, in our problem, these are ordered in the same way. So I know that the first point is like your hand, the second point is your fingernail, or whatever. Then I first compute C using this formula that we derived. I compute its SVD, and then R and T, I can just write in terms of those objects. Cool? Incidentally, the iterative closest point algorithm essentially solves the same problem, but with a weaker assumption. So in ICP, this is not insane clown posse, it turns out. The ICP algorithm takes just 2 point clouds as input, but it does not assume that the points are marked in pairs. So I have to, this assumption that like I can compute this norm doesn't make sense because this I and that I no longer agree with one another. So what the ICP algorithm does is it says like, well, maybe a reasonable guess of that map would be for every point in my point cloud, just find its closest counterpoint in the other guy. And then it solves, and then you can solve this problem. You can solve Procrustes problem. And then you rotate, translate your point clouds to be a little closer than they were before. But now your closest point might have changed, so you update that map and you iterate. That's called ICP. It's a very popular algorithm in computer graphics and vision community. ICP is one of these algorithms where if you read the theory about its convergence, it initially feels very strong, and then if you kind of squint to the theorems, you realize they kind of say like ICP works so long as you initialize it with the solution to ICP. But they're, like essentially it's very useful if you have like a pretty good initial guess of the alignment and then it can fix it. It's not so good if they're like this input here, it would almost certainly fail. There are like a lot of local optima in this problem. I got so excited. A year or two ago, I went to the dentist, and for some reason, they purchased this 3D scanner, and you could see it in action. They were like dragging this thing around in your mouth, and it gets like these little sides of your teeth, and it's gluing them together and registering all at the same time. It's a fantastic example of ICP problem. But I digress. So I encourage you to all go to the dentist. Okay. Right. So that's that. We have one additional application of SVD. I think we won't do this one in detail because like enough already. But just to return to the story that we actually started with for eigenvalue problems a couple weeks ago, let's say that we collect a big collection of data points xi, and now we want to approximate them by extracting the relationships between the different coefficients in our vectors, right? So in other words, like maybe oftentimes humans have blood pressure that's 3 times their weight or something like that. right? Or like there's some low dimensional subspace where this data lives, then we already showed that essentially if I take my data matrix and I multiply it by its transpose and compute the principal eigenvector, that gives me a good one-dimensional subspace. This is actually our first motivation for eigenvalue problem. And in fact, that logic, thanks to the Eckert-Young theorem, extends really cleanly, and in particular justifies this principal component analysis theorem, which basically is just a generalized version of that fact. It says that like if I have to take my data and project it onto a low-dimensional subspace, the best way to do that is to compute the top k singular values of my data. So the book has a little more discussion of that. I think in the interest of time, we're gonna skip for now. Okay, so here's actually one kind of fun application of that in computer science domain. These days we use deep networks, but before some of the state-of-the-art face recognition tools were kind of funny. It was called eigenfaces. So you collect a big data set of people's faces all kind of aligned in the same way in the photograph. And each one of these things is a data point in a very high dimension, equal to the number of pixels in the image. And if you do PCA on this, it turns out that like there's a relatively small set of axes, approximately, that describe most people's faces, which is surprising. And so a relatively kind of clean way to compute identity is to compute those PCA coefficients and then just compare them in L2. Very efficient. These days, I'm sure deep network would outperform this strategy, but this was actually a pretty reasonable starting point. In fact, actually in computer graphics, they have a technique called blend shape, which is precisely this, but instead of pixel colors, they have vertices of a face mesh. And that actually is used in production. I think a lot of times when you see talking head videos that are 3D models, it's really just PCA behind the scenes. Okay, so I thought I would conclude today's lecture. First of all, congratulations, we can celebrate. We're finally done with numerical linear algebra. We're done, I promise. Starting next week, we're gonna do something nonlinear. Mildly nonlinear, but nonlinear. So I thought just to kind of recap our discussion, I'd remind you of some of the notions that we have here and some of the things that you should be sure to remember as you study for your midterm and go out into the broader universe and apply your newly found numerical linear algebra skill. I think essentially what we've done so far are just dressed up versions of two problems, right? We talked about solving linear systems of equations like ax equals b and solving eigenvalue problems, ax equals lambda x. One thing that's important to notice is that these are two different classes of problems, right? And one way to kind of figure that out is that like the unknown in my first equation here is linear, right? Like so it's linear in x. But the unknown in the second relationship here, it's actually quadratic. Do you see that? Because x and lambda are unknown and they're multiplied together. So this is actually a quadratic system of equations that we've been studying. So secretly, actually, we've been solving nonlinear problems the last couple of weeks. We just didn't know it. If when you say linear problem, what you mean is solve a linear system. We talked about Gaussian elimination, which of course is basically just a codification of the algorithm you probably were already doing on paper for solving this stuff. And moreover, if you kind of keep track of all the steps, we noticed that we can write them in terms of these elimination matrices, which led us to an object called the LU factorization, which is basically just like somehow remembering the steps of Gaussian elimination. One thing to note is that the LU factorization is sort of not physical. Like some matrices, like for example, the eigenvalues of a system are like a very physical object. Like if I take a physical dynamical universe and discretize it in some linear algebra language, the eigenvalue is a very canonical thing. It tells you about like the low frequency behavior or something like that. The LU factorization is not the case. I mean, this is sort of just a byproduct of numerical algorithm, right? In particular, like if I reorder the rows of my matrix, I'll get a very different LU factorization. So it's somehow not a very canonical object. But it's useful nonetheless. In particular, it allows us to solve a linear system in quadratic time once we have computed LU. Yeah. A special case of LU is of course, Cholesky factorization for symmetric positive definite matrices. This one we're going to use in several different contexts moving forward. In particular, in a couple lectures, we're going to talk about the conjugate gradient algorithm for solving linear systems of equation. We're actually going to kind of apply some of our thinking about nonlinear problems back to the linear universe and show that it brings some insight. And the way we're going to derive it is actually by plugging in a Cholesky factorization, deriving conjugate gradient, and then showing that Cholesky was not actually needed. It's kind of sneaky. I just think it's one of the more direct ways to derive this thing. We talked about QR. So remember that QR is all about the column space rather than inverting a matrix. and like computing a basis for a set of vectors. And then finally, we talked about eigenvalue problems. We started by diagonalizable matrices and then ended with SVD. Okay. So in any event, like I say, that's a very high-level list of topics to kind of study. And of course, hopefully what I've convinced you guys is that these are very computable objects. The algorithms for computing them are all built into like Python and MATLAB and Julia and whatever programming language you prefer. So you probably don't have to code up any of the things that we've covered so far. And that's actually reflected in the coding problems in your homework, right? Like, I didn't ask you to code up Gaussian elimination in your homework. In fact, if you did, you probably did something wrong. But rather, like, we kind of view these things as clientele. And then when we talk about engineering numerical algorithms, it's more like what we did on the board today, like taking a messy problem like point cloud alignment and showing that it reduces to one of these sort of canonical objects. That is the art of numerical linear algebra. The art of optimization is that optimization is messy and there's a billion algorithms and we're going to struggle with that. That starts in our next lecture. Okay. And of course, the themes here are that we can look for all kinds of nice special structure in our matrices to solve these things efficiently. Reducing our problems to known algorithms is how we did basically everything. Like in a sense, we've only solved like 4 problems in this class, right? We only know how to do like what? SVD, eigenvalues, matrix inverse. That's about it. But yet, of course, that's extremely powerful and lets us solve a wide variety of stuff. And that when we solve any of these problems, we need to evaluate their stability and conditioning to make sure that our algorithm actually is expected to produce a reasonable output. Yeah. Like you might notice we spent a couple lectures on like number systems and rounding and all that stuff, and then sort of we quietly moved on to these algorithms and never talked about it again. Like we assumed that our computational system kind of has infinite precision, and the discussion we did, like for example, of SVD, you might go back and kind of view what the effect of a finite precision arithmetic system is going to be on each of these algorithms. And one way to do that is by understanding stability and conditioning. Like if I get every calculation a little wrong when I do my math, how much can I trust the output of an algorithm that otherwise would be correct? Cool? All right, so I think we'll call it for today. I know you all have homework you need to finish off. So we'll hang out and have office hours outside of my office. I might, depending on how busy they are, I can try to defray the craziness for a little while. And then your next homework is out, and I will see you on Tuesday. Whew.